Hello everyone. I'm gonna present my project called Deep Q Learning Implementation for Atari games. The games which I chosen is River Raid, and that is present in the Atari games. So in the next few minutes, I'll walk you through my deep learning project that trains an AI agent to play the Atari River Raid using Deep Q Learnings. So here's what I'll be covering today. First, I'll explain the complete workflow from environment setup to final evaluation, showing how we transform random button mashing into intelligent gameplay. Second, I'll dive into technical architecture, including the DQN network, a GPU optimized replay buffer, and custom environment wrappers to make that learning possible. Third, I will demonstrate the hyperparameter optimization process that identifies the best configuration from multiple candidates. Then I will show you the actual training progression with real metrics and learning. Finally, I'll present a detailed result analysis comparing our train agent against baseline performance, showing exactly how and why we achieved that improvement. Throughout this presentation, you will see the actual gameplay footage, performance charts, and the specific engineering decisions that made this implementation successful. Let's begin with this technical workflow. So the project follows a systematic six-phase workflow. The phase one would be the environment setup using the gymnasium with custom pre-processing. So here we can see, so this is our river rate, and the environment setup includes the required package installation, which are a gymnasium, torch, and ALE. So these are the three main packages that are required here. Then after installing all these steps, we are going to import the libraries and set up the necessary GPUs in order to make use of the GPUs as well. So here you can see right now I run with the CPU, but if we need to use the GPU, we can use the GPU as well. Then the next one would be presenting the custom wrapper implementation. So this wrapper implementation gives the -100 penalty for the life loss, teaching self-preservation, and also it takes all the game scores which are shooting a ship, jets, and other things will give you a positive points, and then shooting the fuel will give you a negative points, and losing a life will give you a -100 penalty, which is a huge. But this is needed in order to train the uh, deep learning concepts as well. So the next would be getting the fact environment to function. So we are going to create an environment which is from the gymnasium. Previously, it's called a gym, but right now it's called gymnasium. So that's the newer version of it. So both are same, but since we are going with the new version, it will be much easier. So I'm gonna initialize the evaluation and video recording function where after the training is completed, so it will evaluate based on the results and then it will give you the video footage of the game it played. So that will be present in the Google Colab itself in the cell output. So that would be a great way to show our model that it played well. Then we are gonna have the evaluation with the random agent. So random agent is that it gives the couple of actions to the environment and it will see how the game played. As you can see, so this is the game it goes. So it took the best score as 1540 and 1254 is the average score. So we have tested this game for the random movements and we are gonna implement now the DQN architecture. So there are like three convolution progressive scores which are like 32 filters, 64 and 64 and these are the kernel sizes for the DQN architecture as well. So this uses the DQN architecture with 1.67 million parameters, separating value and advantage estimation. So here you can see it uses all the GPU usages and it uses the memory flow optimization as well, so that it runs very efficient on those GPU and as well as on the CPU. So I'm implementing the replay buffer as well here. After implementing, the next would be like action selection and the training loop. So this is the main architecture that has all these things. Then the next step would be hyperparameter configuration. So first we are gonna get the best parameters of the uh, like of the architecture, and then we are gonna use that to train our full model. So right now I'm using four different kinds of hyperparameters. So one is the standard, aggressive, patient, and explorer. Here you can see I'm tuning these four parameters, which are learning rate, gamma, alpha, and epsilon final. So after giving these ones, so these are the full configuration of our DQN architecture. So the main thing you note that we are having a buffer capacity as 50,000, and the number of episodes which we are gonna run is for the 1,000 ones, and for every 4,000 we are gonna get the target updated. So the learning starts as like 20,000 because we need to initially first run for the few steps and in order the model to train it, and then we can go ahead with sorry, first exploring, and then we need the model to train it as well. So after running the hyperparameters, the best episode will be present here. Then we are gonna have the base model training, which is like without any learning, we are gonna train the give the scores of the model. So that model we have the score as 913, which is the average score. So which is before the model training here. So we're gonna implement with the parameters which I used from the hyperparameters, and then we are gonna use that one. The next one would be memory optimizer hyperparameter search implementation. So after implementing, we can find that the best configuration is the learning rate is double triple zero two five with these hyperparameters. As you can see, so these are the average rewards for each and every trial, and we can see this one has the good results as well. Then we are gonna use that parameters to train the full model. As you can see, for every training steps we have split into average rate and the loss and the steps taken to complete this and muscle. Then we are going to visualize it. So this is the entire visualization which we got. So these initial parameters, because we train the agent to do the uniform explanation, that's why we have a very uneven rewards. And then once it start learning, it progressively increases. And it's the same for the training loss as well, because once the model gets learned, it will get all the details for it, and then it will produce the results, and it means that it's learning from the game. So the evaluation would be after doing, we are giving final evaluation for the train model. So I'm gonna play a game. So this is the model which play in the game. As you can see, it passes through very well, and it has the maximum score of 2210. Now comparing all these results, we can find that so the green would be the train model. As you can see, them all the scores for the train model is very good compared to the random or the baseline models. So as you can see, which is very good, and it has trained from the model. So for now, since we played for the 1,000 episodes, and in the future, if we are going for the other episodes, so I think it will learn even better. So as you can see, like the project successfully demonstrated that deep Q learning with the significant achievements. The 30% performance improvement validates our architectural choices. So, key technical contribution include the GPU optimized replay buffer, two-phase strategy, and other things as well. Uh, this project demonstrated that successful in reinforcement learning requires not just an algorithm, but careful engineering of all these components as well. So, thank you for watching, and all the codes and everything is present on my GitHub. So, feel free to check the entire one so that we can have further topics. Thank you.